Yeah. Hang on just a second. I just need to, okay.
How else are you gonna do it? Oh, okay. Gotcha. I don't think it should be that bad because they're really for the most part. I used to play this semester. Just two. She will or will not. Oh, except two. Yeah, I don't know what we were both in that class.
It wasn't fun.
That's what I was supposed to do. Never see you do that.
What do you do?
I mean, I am looking forward to it. I'll do a little check.
He's not now wants to watch, he's gonna be the storyline final projected file. Also, it looks like there's a deadline day transfer coming for 3 students to Chelsea.
Have you seen that?
I just replied to your email.
But yes, unlike my battery.
Everyone. Yeah.
That's just two metal plates. You
That's
put
probably
negative
what
charge on
Justin
one
might
side
be
and
getting
it's
them is
negative.
because
Negative charge on the other
I
side.
wasn't 100% sure, but I figured that you were. But
Yeah, you were right.
Yeah, I'm very confused by this. Okay. Okay. So you'll have electric field points later with plus, so there'll be an arrow like C with plus.
No, but there's
And then
posted
more
charge
the
and
minus,
Completed.
so you have.
I wanted to look
So
at it.
you'll have,
Yeah, I'll see it, or I'll wait until I see it.
so you have, oh, is this potential or field? Okay, so rather, yeah, just to think about the direction, like that will tell you the magnitude, but not the direction. So you have plus, minus, and minus here. So, right, there's gonna be an electric field vector that points away from this plus. There's gonna be one that's shorter that points toward this minus.
it's just a few different steps.
Oh, you know what?
And then one that's sort of medium length that points toward that minus. So these will kind of cancel out. This one a little bit shorter.
That's what you're finding.
And you're looking at the limit is the vector sum.
Yeah, that's what I did. I just did the X. I just did this too. So I did that's how I got it. I did this one. It's one to longer than this.
Oh.
She was over here. I'm like, oh, okay.
Yeah.
This one.
Yeah,
Thank you so
okay,
much.
that's nice. Yep.
Thank you.
I'm glad to have some mistakes. Those are good ones to have.
It's hard.
Yes,
I responded to your email last night with that.
that looks great. Yeah, I like to give it a day so I can reread things, but I have it ready. And they emailed me like a few days ago with a place where I can go for the link. So you're all set, barring, you know, major life-ending accidents on the way home. You'll be good to go. Oh, well, you all can't see me now. Oh, grab my notes. Okay.
Where is this?
Oh my goodness. There it is.
Yesterday, my 2-year-old had to go home sick from daycare. He's been there ever since, which means that I have been home, not at daycare. I did not grade your labs this week, so everyone gets full credit, but I haven't looked at these. So be sure to make sure if there's things that you weren't sure about. I'll make sure as soon, I think it might not be up yet, but as soon as I get a chance to go and put my solutions up, if you are unsure about any of the uncertainty type things on this, make sure you go check that out, because your homework this week, if you haven't noticed, is the same set of error analysis calculations that you did in lab, but for a different line on the data table. So all 4 of the groups emailed me a photo of their data table. If you didn't get your data table, I can probably email that to you. I also have my own data table that you're welcome to use. It's up with the Lab 2 materials. That's fine too. Just make a little note that says that that's the one that you used. But that one is totally fine with me if you used this. Turns out I've done all the analysis on that data table, so I know all the answers. So it makes it even easier to do grade. So that's fine too. Okay, so let me get these back.
There you go.
No, honestly though, I feel like, my learners, Marcus Alonso, was left feedback.
Okay, so if you're still working on the chapter 16 homework and you're stuck on a couple of things, I'm here until like 3:20 today. Let me just like reset myself and calm down. Okay, so I'll be here for about an hour after class. I'm happy to answer questions. Posted up online, I have the 3 practice tests posted for your test 1. So a week from today, you're gonna come and there will be the first test. I think it's worth 10 or 11%, something like that, of your grade. So we have 4 tests in this class, just like we did last semester. None of them are worth a lot, but it does keep us constantly testing. So what is posted right now is 3 practice tests. And the 3 practice tests, just like I did last semester, I make 4 tests. And 1 of them is your test, and 3 of them are practice tests. So in terms of format of the test, type of question that's on the test, degree of difficulty, all of those things should match the practice test really well. I will remind you that you learn like so much better if you're given the opportunity to miss questions. So the worst way to study is to print off the answers to the practice test and then look through them and try to memorize them. That does not teach you anything. Because the only thing that I can guarantee you is that none of the questions on the practice test will be on your test. So it's the way that you think on the practice test that trains you for the test, not the answers to the questions on the practice tests. So sit down, test yourself with one in the beginning, and see how you do. Identify some places where you need to check, and then sit down with the next one and test yourself after that. And if you really want to go for it, then sit down with the third one, and test yourself with the third one. You're not under any obligation to use all 3, but I figure that's about as much as anybody could want. So that's with that. Lab 3 will go up later today. Again, I'm behind on all sorts of things from the last 2 days of wiping snot off of faces and trying not to let it infect me. And so that will go up later today. And I think those materials are just about done. So questions? Bring a 3.5 by 5 note card to any test that you will ever take from me in this class. So that includes this test, any of the other tests, and the final. So you can write anything that you want on it, front, back. Go for it. All the stuff that you think is going to be helpful goes on there. Okay. So we don't start there. We did that last time. So where we are today is here. So what we started last time was we introduced this idea of potential energy, thinking about potential energy as the ability to do damage. So where things that might make a lot of damage are is where there's high potential energy. So like charges all clustered together have a lot of potential energy. And we also introduced this concept of voltage. And so I want to see how you're thinking about this with this question. So look at it for a minute and see if you come up with what you think. Maybe share that with the person next to you and then we'll go over it. So what does the proton do? It doesn't remain at the dot. Why does it not remain at the dot? It's at 0 volts. Shouldn't that be remains at the dot? Why is that not the answer? Yeah, there is a force. Okay, so 0 volts is like saying that the elevation, your elevation is 0 feet. Okay? If you're standing at sea level, that doesn't mean that there's no slope to where you're standing. Okay? You could take this thing and try to think about this as being a sheet. What we are saying is that this location here is elevated relative to an undisplaced sheet. This location is right where the undisplaced sheet would be, and this location is negative relative to an undisplaced sheet. Okay, so it doesn't really work geometry-wise for you to try to do this exactly how it is on the screen. But if you can kind of imagine it looking something like this, where up here on the top, this is the plus 50 volts. Down here on the bottom, this is negative 50 volts, okay? And if I put a ball right here at 0 volts, it would roll down the hill, okay? What would happen to its speed as it rolled down that hill? It would speed up as it did it, okay? So the undisplaced sheet looks like this, right? So there's 0 volts. So voltage, potential, electric potential, those are all words mean the same thing. In my mind, I think about, that's an elevation. Right, that's where the undisplaced sheet is. So 0 volts is here, and what we've done is that, okay? So what's gonna happen if you put that dot right there, and we're putting a proton right there, so the proton does what our intuition about gravity would say, which is that it's gonna roll down the hill. So it's gonna roll from high potential, high elevation, down to low potential, no matter where you put it. Okay. Okay, so what I want to do is make a table that helps us get an idea about what we just talked about for like how positive and negative charges would behave if they were placed in a potential field, kind of like if they were put on a sheet somewhere. Okay, so let's talk about a positive test charge. And we'll put that here. And over here will be a negative test charge. And this is going to be a positive test charge moving from high to low potential. And this will be something moving from low to high potential. Okay, so this is the one that we just did. We had a positive test charge would move on its own from high to low potential. What happens to its potential energy as it rolls down that hill? It goes down, right? Just like the ball rolling down the hill, being at a lower elevation. So the potential energy has to go down, okay? What does that mean the kinetic energy has to do? It has to go up. Last semester, we always used to talk about having to ignore friction and air resistance and all of those and like live an idealized physics world. We still have to do that, but it's a lot easier when we're talking about these really like microscopic scale things. So friction and air resistance aren't nearly as much of a big deal as they were last semester. And this is the fact that there's no non-conservative forces acting here is a way easier assumption to make here. We're not really skirting things under the rug. That very much so is that potential and kinetic energy is all that's there. Okay, so it will roll down the hill, it'll lose potential energy, it will gain potential kinetic energy, and so this says it speeds up as it rolls down the hill.
I tried to write, it speeds up as it rolls toward lower potential, right? It's going toward lower potential. And our analogy with the sheet is that that's down the hill. Okay. So a positive test charge does this. The negative test charge, where does it speed up? If you make the negative test charge go down the hill, it doesn't really want to do that. What a negative test charge wants to do is roll up the hill toward higher potential, and it will speed up as it does that. So over here, I'm going to write basically the opposite of what I wrote here, down here. So, or the opposite is even the wrong word to say. I'm going to write more or less the same thing that I wrote down here. So the negative test charge will, these should look the same. So it loses potential energy, it gains kinetic energy, and it speeds up as it does it. So what I mean by that, and maybe something that might help with the visualization of that, is if this is the potential, I have high potential up here and low potential down here. You know, the high potential means that, right, if we were to assign charges, this is where the positive end is, and that's where the negative end is, okay? So if I put a positive charge right here, the reason it rolls down the hill is because it's attracted to the negative charge down on the low potential end and repelled from the high potential, the positive charge up here. Okay, but a negative charge put right here feels exactly the opposite force, right? It's repelled from the negative charge, so it will actually roll up the hill toward the positive charge where it's attracted. Okay, so everything makes sense in gravity in this row right here. Everything is opposite of what you'd expect from a gravity kind of an analogy down in this bottom row.
Wait, so I don't understand why the potential energy decreases.
That's a good question. So, well, you're a negative charge on this hill. Where do you have more ability to do damage? A negative charge right next to a positive charge? Is that high or low potential energy? That is low potential energy because the negative charge has the least potential to do damage when it's right next to the positive charge, okay? You put the negative charge all the way down here next to the other negative charge, and that is low potential, but high potential energy. Does that make sense? Right, and this is an exact analogy with that electric field and electric force point in the same direction for a positive test charge, and they point in opposite directions for a negative test charge, right? The same thing here, right? The positive charge moves towards high potential if it's positive, but it'll actually move toward low potential if it's negative, okay? All right, so let's go back to our positive test charge. Low to high potential, roll up the hill. Okay, so it obviously won't do that on its own, but if we gave it some external force, you know, if it's a ball, we kicked it up the hill, it would go up the hill. What would happen to its potential energy as it went up the hill? As it goes up to the top of the hill? Yeah, it goes up. So potential energy is higher up at the top of the hill, which must mean that its kinetic energy had to go down, which must mean that it's slowing down as it rolls to higher potential. All right. And now we have one left to fill out. Maybe you're kind of seeing the pattern. We're going to more or less copy what we did over here, which is that negative test charge moving from the top of the hill down to the bottom of the hill right, is what it would do naturally, or say that backwards. Yeah, the negative charge would not do that naturally, right? It wants to be up at the top of the hill. So as it rolls down the hill, it's going to lose potential energy and it's going to gain potential energy and lose kinetic energy.
So potential is still a vector, right?
Potential is not a vector.
Although the charge has a sign.
Huh?
Although the charge has a sign.
So you can have a sign and not be a vector. So work is an example of something that has a sign but not a vector.
Okay.
Right? You can do positive or negative work on something. Just like you can have positive or negative potential. Just like, I'm going to keep making this gravity analogy, just like you can be above or below sea level. So you can have a positive elevation or negative elevation. Okay? Okay. I'm hoping that this is starting to feel a little bit less weird. I think I said this on day one, but it's the reason that this semester is hard is because we have no intuition about what charges do and how they behave. So developing that intuition is the hard thing about this semester. How to do? I think I did okay. So hopefully that matches just what we wrote here. And I think I wrote here, electric potential, so that's voltage, V, and electric field aren't two different things. Instead, they're two different perspectives on this sort of thing. So here's where the high potential would be, and here's where the low potential would be in this diagram. We've sort of left electric field off of this. And if we had a positive charge here and a negative charge here, and that was sort of like what our field looked like, right? There would be the high potential. And there is our low potential. And we know that electric field lines always point from plus to minus. Okay? So these electric field is like how steep the terrain is. And potential is how high you are. So V is how your elevation. And we'll do more practice with this, but I think if you can really internalize all of this stuff, you'll be well on your way.
So when we use a negative test charge, but we say it goes from high to low potential, are we still talking about high potential means like the positive to the
Yes. Yeah. And what every single one of you will do, if you haven't already done it plenty of times, is matter that much. Because high potential energy is high potential. Right? A positive test charge up here has high potential energy. So just like the E to F thing, right? Everything makes sense if it's a positive test charge. But if we're talking about potential, the high potential is always up here, whether or not there's a test charge.
So in this case, the potential energy near the negative end is higher.
The potential energy would be higher if there was a negative test charge,
That's what I'm saying.
and it would be lower if there was a positive test charge.
Are we
Yes.
saying potential energy increased as it goes? Okay.
As a negative charge went up the hill and got farther away from this negative charge,
Or decreases?
it will go down. Right?
Okay,
Its
so it's
ability
not
to
the
do
way-
damage will go down.
Okay, so, okay.
You definitely gotta think through it.
It always makes sense though to say high potential, high voltage. Right?
Yes, the voltage and potential are two words that mean the exact same thing.
The physicist will say potential, the electrician at your house will say voltage. But those two things mean the same. Okay? And because it's measured in volts, even the physicist will often say voltage. Sometimes in the same sentence, just because they're being difficult. And not intentionally difficult, but just because, right? Like in my head, those two words are so synonymous to mean the same thing that I might accidentally say two different words in the same sentence and you know that I mean the same thing.
Some scholarly.
Yeah. I don't know. If scholarly just is like code word for designed to be difficult, then sure.
Sorry, I've been thinking about this. So hypothetically, we could assume the two charges have exactly the same magnitude. So one positive charge up the hill and one negative charge down the hill. And they have exactly the same magnitude, and one is down just because one is positive.
Okay, yeah. Okay, thank you. Then,
How is so when you say how steep the terrain is, how does that perspective apply?
how does that apply? How about this? A capacitor where this would be the positive end and that would be the negative end. Okay, so the electric field is like how steep the terrain is. So here's a visual demo of that. Where is the electric field stronger? The sheet looks like this, or the sheet looks like this. Okay, right. So this is a steeper sheet, which must mean that there's probably a greater amount of charge on my two plates. So I get this strong electric field by having a steep sheet, by having steep terrain. Okay, but on this parallel plate capacitor, and it's one reason that I like talking about a parallel plate capacitor, because it's simpler than the point charge. Right, the electric field strength is the same everywhere. Right, this isn't steeper down here or up here. Right, it's not that the electric field is biggest here. The electric field is the same here as it is down here. Right, it points downhill. It's a constant all the way down the hill.
So it doesn't matter at all, even the magnitude of the negative charge is much larger than the magnitude of the positive charge. It's still called high potential because positive.
Yeah, this would still be the high potential.
Even that's
Right, so potential on this sheet is not constant at all. Right, this is where the high potential is, this is where the low potential is. So the potential is the elevation, right, how high up you are. But the electric field is the same everywhere on this sheet. When you do, and now this is gonna work as well, but I can show it on the screen. Yeah, my sheet works very well for a, there we go. So for a point charge, this is above 0, so this is all positive potential. Okay, and actually this kind of goes out infinitely far away, technically, all the way out into infinity. It's going to be ever so slightly above 0, as long as all that is there is that positive charge. But so if we think about electric field, where is this steepest? I think I heard the right thing. It's way steeper out here than it is down here. Okay, and if I were to think about like drawing the electric field, right, like the steepness of the terrain is very steep here, and then as I get farther and farther away, it's leveling out and out and out and out. And the steepness, right, my arm being kind of a measure of how steep I'm going here, is getting shallower and shallower and shallower. And that fits with what you know, which is that the electric field is strongest close to the charge. And the farther away you get from the charge, the less force a charge that was in the vicinity would feel, and the weaker the electric field is. Okay, all right. Okay, this is maybe not an exact follow-up on what we were just talking about, but still another good one. So we did this as a question in chapter 16. So we said we wanted to figure out the direction of the electric field at the dot. And I'll remind you what we did. So we said electric field always points away from positive charges and toward negative charges. So here's the dot. So I'm going to cover up the negative charge and just think about the positive charge. Away from the positive charge is like that. Toward the negative charge is like that. And we had these two charges that must cancel each other out and end up
pointing to the right. You remember that question? Okay, and I think you got some extra practice on that question quantitatively in your homework this week. Okay, so a small positive charge on the dot. What does a small positive charge here feel for the force? The same, okay? So a positive charge, the field and the force point in the same direction. So that would be to the right. Small negative charge at the dot, what direction force would it feel? To the left, because for a negative test charge, the force and the field point in opposite directions. So that's to the left. What about the potential? Is the potential at that dot positive, negative, or zero? That's a harder question. It's just a different question. Oh, thought that was gonna show my visualization thing. Is that right? Yep, I think that's the right one. So here is what this looks like, where I had a positive charge on the left and a negative charge on the right. I'm going to move this so it looks a little bit more like what it was looking like on the screen. You can kind of see what I'm talking about. So I had a positive charge over here and a negative charge over here. So everything close to the positive charge has to be potential what? Greater than or less than zero? Yeah, so it's above zero here. Everything closer to the negative charge is less than zero. And there has to be, do you see it? Do you see this little line right here? That's the line of zero voltage or zero potential. It's sort of dividing the left-hand side where everything over here is plus from the left-hand side, or the right-hand side where everything over here is minus. I can change these colors. I'm going to change the color instead of being, I think they were currently set to field magnitude. So a darker green is a stronger electric field. Now I'm going to set the color to be potential. So you can see the green is plus now and the red is minus. And it's sort of shaded everything gray as being close to zero. But there's really just this one spot right here where you're equally far away in this dot from the plus and the minus charge everywhere. That cancels out. You're at that zero elevation line.
How come the second one points to the right?
Fields of force pointing in the same direction as the electric field. You could do the same sort of analysis though and put a plus here. And now instead of thinking about electric fields, you could think about forces. A plus and a plus, that's a repulsive force. So that would be F plus. A plus and a minus, that's an attractive force. So that would be F minus. And you get the same thing. It's zero. Okay, so there's an example of a place, I'll get you just a second, okay, where the electric field is not zero, but the potential is zero, okay? So you can be at zero elevation and still at a place where there's a slope to where you're standing.
So from the chart, because it's just staying at the dot, but if it were to move too low, then it's negative.
If it were to move too low potential, then it would be negative, yeah. And that's what you see in this thing here, is what all of them are doing, right, is they are rolling downhill, right, in the direction of the electric field lines. They're rolling fastest where it's steepest and slowest where it's less steep, in that same way, yeah. Okay. Okay, so a couple of real life applications of potential. This how lightning happens because air is actually a very good insulator, right? It doesn't conduct charge. But if the potential gets high enough, then it can actually ionize the air and turn the air momentarily into a conductor. So what ends up happening with air, with snow, is that the way snow develops is actually somewhat similar to the way that rain develops. It aggregates. So what ends up happening is that the way snow develops is actually somewhat similar to the way that rain develops. It aggregates. So what ends up happening is that within the cloud, there's snow that is near littler ones. And just like plastic rubbing on wool, these things are frictionally charged. So by that I mean, like when they bump into each other, when they rub in with each other, they'll turn two neutral objects into charged objects. So they can share charge in that way. So what tends to happen is that when they bump into each other, and this is where I have to look, the lighter particles tend to gain these positive charges, and the heavier particles tend to gain these negative charges. That makes them attract, and so this will get stuck on there. And they can grow depending on how kind of extreme the conditions are. But in really pristine conditions, you can like see how they grow in this really cool hexasymmetric shape in that way. And if you are in a thundercloud, chances are there's a lot of air going up. We call them updrafts. And it carries these littler snowflakes up. But it's maybe not enough to quite counteract how heavy the bigger snowflakes are. So the bigger snowflakes still fall down, but the little snowflakes, they're like feathers, right? Where air resistance is just too much. So these bigger ones get put all the way up at the top, or the little ones move all the way up to the top. The bigger ones move all the way down to the bottom and accumulate as snow. And meanwhile, they're kind of colliding with each other and sharing. And accumulate as snow. And meanwhile, they're kind of colliding with each other and sharing charge. And that's how you end up with this really big charge separation. Yeah.
Does this have anything to do with why, like, when it thundersnow, the moment lightning strikes, it almost seems like the snow like just falls in a sheet for a second?
I have no idea. But I will say that this is what makes thunderstorms in the summer. You don't know it, but ice and snow crystals are in those clouds. Like it's way above ground. It's freezing. Snow, and actually you can tell if the cloud has ice crystals in it by looking at the cloud. If you look at the edge of the cloud and it looks really distinct, like you can tell white from blue, it's like a really clear line, then that's an all liquid cloud. And it's very unlikely to make thunder. It's just not a very big cloud. But once it gets deep enough in the atmosphere where the really high, really cold temperatures are, it turns into ice. And then the edge of the cloud just gets quite a bit fuzzier because the ice and the snow kind of they just look fuzzier from far away. Yeah.
Is it the same for tropical countries where there isn't any snow?
Yeah. I mean, like tropical country, yeah, like the deep thunderstorm convection clouds go like 15 kilometers, 10 miles or so high up in the sky. Like no matter how warm it is down at the surface, I promise you it's way below freezing, 10 miles high up. So yeah, like proper thunderstorm clouds have lots of ice in them. Yeah, someday maybe I'll teach a weather class, but not today.
Okay, so you end up with this separation of charges. And when that separation of charge gets to be about 10 to the 8th volts or so, then that voltage is enough to cause the air to break down, and it makes lightning. The same thing happens inside your the cells of your body. So I think most of you talked about the membrane potential in other classes. This is basically my 100 level understanding. This is basically how nutrients get in and out of cells. Yeah? Close enough? Right. So the way that, and we'll talk more about this actually when we get to talk about capacitors in a couple of chapters. The way that this works is by setting up a potential difference that makes charges that maybe wouldn't otherwise, or charged items that wouldn't otherwise want to end up in the cell, pass through that because they're in this electric field that's causing them to rot. And this is actually a picture of what it looks like to measure the membrane potential. So there is like this is a cell. And so there's a probe going into the middle of the cell, and there's some other probe somewhere just out here, outside of the cell. And you can use those two probes, much like you would use the probes that we're gonna use in lab next week, to measure the potential of a battery, to measure the potential difference, so the difference in voltage between the inside of the cell and the outside of the cell, and that's like 70 millivolts, which doesn't seem like that much. Millivolts is a very small number, but as you well know, cells are very small, so that potential difference over really short distance is actually a huge electric field. That electric field that's inside your cell would be more than enough to ionize air. It's a very strong electric field that's setting all that up.
That happens very fast too.
No idea.
Is it because like voltage is how things move, so you have to like complete the circuit to see